Hello grade 12s, and so today we are going to look at electrical machines. So what that means is we're going to look at motors and generators, and it follows on from some grade 11 work, which I know feels like a lifetime ago, but it's alright. Guys, this is another section I guarantee you either a motor or a generator question. It's one of those things where it's going to come up. Please don't think you can skate over it because you can't. So first thing we need to do is only really 4 important words here, and that's generator, motor, AC, and DC. So those are the terms. So I'm going to give you 2 minutes, and I want you quickly to discuss amongst yourselves what those words mean or what those terms mean. Okay, so your 2 minutes start now. Okay, grade 12s, I'm hoping there weren't too many issues with this because these are terms you've heard along the way, like AC, DC in terms of current and all sorts of things. So I'm hoping there weren't too many issues, but hopefully by the time we're done with today's lesson, we will all be fine with this. Okay, so electrical machines, like I just said, are broken down into 2 types. Okay, so we have our motors and we have our generators. Now, they all come down from the concept of electromagnetism, which you did in grade 11. And remember, electromagnetism, the first part of that is the fact that if I have a current in a magnetic field and there's a change in the magnetic field, the conductor or the wire will move. That's the motor effect. That's what we use when we look at electric motors. The opposite of that is then true because scientists went, well, if a moving magnetic field, if we have a current and a moving magnetic field and that creates motion, surely motion between a coil and a magnetic field should also create electric current. And that, of course, is electromagnetic induction, which we use for generators. And everyone's electricity supply is based on a generator. The only way to create electricity that doesn't rely on a generator is things like solar panels. Okay, they don't use generators. Wind turbines, water turbines, any of those, they all use a generator. They all use a turbine of some sort, which then goes to a generator. So when we talk about alternative ways of creating electricity, we're just talking about alternative ways of turning the turbine. Okay, and of course we all know that's really, really important. And even in a country like ours, which is very coal rich, we are going to run out of coal eventually. So we have to find alternative ways to create our electricity. Now, the thing here is that a generator and a motor are very similar in their setup, and they can either be DC or AC. Okay, DC means they can work or produce direct current, or they can work or produce alternating current. The biggest difference is a very important thing. In AC generators and motors, we have slip rings. In DC generators and motors, we have a split ring commutator. These two terms are vitally important, and you cannot get them confused. Okay, so let's go back to motors. The thing about a motor is, what do we need? We need a current and a magnetic field. Okay, and the thing here, and this is what we learned last year, is as the current moves through a conductor, the current creates a magnetic field. The magnetic field that it creates interacts with the magnetic field that the conductor is in. That interaction is two forces. They're non-contact forces, but they're still two forces. Those two forces make a resultant force, which then makes the conductor move. So what I have here is an example. So we have a magnet, okay, or two sides of a magnet. Remember, magnetic fields always go from north to south. Always, okay? And what we have here is, if you look carefully, there's a little ring around the conductor, because remember, use the right-hand rule. Around a conductor creates a circular magnetic field. That circular magnetic field interacts with the magnetic field from the magnet, and we'll pretend I can do things in 3D because I'm amazing, okay? And that interaction causes the conductor to move, okay? And the conductor is either going to move, in this case, in or out of the magnetic field. Now, how we determine the direction of that, this all depends on what your teachers have taught you. And there's no particularly wrong or right way, okay? So some of your teachers may have taught you what is known as Fleming's left-hand motor rule. Some of you might have been taught the right-hand rule, okay, the right-hand palm rule. It doesn't matter, grade 12. So I'm going to do both, okay? I personally like only using the right-hand one because it's only one hand, and two, I'm right-handed, so I know it's the one I write with. So therefore, I'm always going to be right if I use the right hand. If I'm left, it gets confusing. Anyway, with Fleming's left-hand motor rule, the thing to remember here is when you're learning to drive, you change the gears on your motor car with your left hand, okay? If you're trying to change it with your right hand, you have a left-hand drive car and you're in America. Okay, we're not there. Anyway, point is, if we use Fleming's left-hand rule, we have our left hand pointed like a gun. My thumb is the force or the direction in which the conductor will move in. My finger, this finger always points to south. It's my magnetic field. And my middle finger points in the direction that the conductor's moving, the current in the conductor's moving in, okay? So if we look over here, so we go back to the problem I have here, and you can see now what happens is if I do it down and you looking at it, you go, well, we're going from north to south. That's the direction the magnetic field's going in. My current is moving downwards, and my thumb is pointing out. And if you look carefully at my diagram, there's an arrow that's pointing out. That's showing you the direction in which the conductor's moving in. Now, let me tell you why it doesn't matter if you use your right hand. Your right hand rule says to me that we have a flat palm, okay? My fingers point in the direction of the magnetic field. My thumb now points in the direction of the current. My palm is the unknown. It's what direction that the coil is going to move in. So now, in your exam, don't do what I'm about to do now because it's going to look a bit silly. You can move your paper around, okay? Otherwise, you all end up doing this and that, and it's particularly funny when it's with your left hand, especially when you guys start doing this. You don't need to do that, okay? But watch. So the current's going down. It's going from left to right. And this one shows me, just like my left hand did, coming outwards this way. Okay? So it doesn't matter which one we use. Okay? It really doesn't matter. The reason why it doesn't matter is you're not going to be asked to state it. So whichever one you've been taught, Fleming's left-hand motor rule or the right-hand palm rule, does not make a difference. I personally teach my learners just to use the right hand, okay, because you get very confused. And some of you don't always know left from right. That's okay. We all have those moments, okay? So what do we need to remember here? In an electric motor, this is very important, a current passes through a coil in a magnetic field. that combines two forces together, which turns a motor. So in the picture we had originally, there was just one coil that moves. In a motor, one conductor. In a motor, we have a coil, okay, which then turns. And we use motors for things like hair dryers, okay, toy cars, fans, all of those sort of things. The big thing here, okay, is that a motor converts electrical energy into mechanical, okay? So we take electrical energy and we convert it into mechanical. So now, in a motor, we have an electric current supplied through the commutator, which we know is a split ring, okay? Now, it's a split ring because it has two halves over there. Okay, we have that split ring, and the reason why we have the split ring is we want the current in the coil to always flow in the same direction. That's really, really important, because otherwise, if we don't have the split ring, what happens is that the coil will do this. It'll go backwards and forwards and backwards and forwards and backwards and forwards, and that defeats the object. We want a coil that's going to keep moving, okay? And it's also it's a hard thing like this, because what it also does is it stops the wires from getting all bundled up and pushed together, okay? And what we have over here is we have carbon brushes, and the carbon brushes maintain contact between the coil and the circuit and the commutator. Okay, so they make sure that there's always contact so the current can flow through it, okay? And even looking at the diagram I've got here, remember, current is conventional current, so it goes through, so it's going to go up this way. You can see the orange arrow, so my current is going from north to south. It's going in that direction, so my palm's pointing down, which means the coil is turning this way around. That's clockwise. Okay, same way the hands go around a normal clock. Okay, all right. An alternating motor. So this motor here that we've got here with the split ring that I just showed you, it's a direct current motor. That means it works off a battery. Okay, an alternating motor works off what we use our electricity supply. The difference with an alternating motor is we have to have two slip rings, okay? Because if we don't have the slip rings, it'll go backwards and forwards the whole time. So with the slip with two rings, it allows it to keep turning in the same direction. So a DC motor or generator has a split ring commutator. AC has to have slip rings. There has to be two, okay? So DC, there's only one ring. AC, there needs to be two. The whole point is to make sure that the current inside the coil goes in the same direction in the magnetic field the whole time as the coil turns. Without them, it'll simply go backwards and forwards, which defeats the object, okay, which is what we don't want. So, how do we make the force stronger? So when we look at a fan, for example, and we want the fan to go faster because it's a hot, hot, hot day, how do we do that? What are we doing when we make the fan go faster? Well, there's a couple of things we could be doing. One, we can make the current stronger. The stronger the current, the stronger the magnetic field that the current produces, the bigger the force. We can increase the strength of the magnetic field. Please be careful here, grade 12s. You can't write in your books or in your answers, use a bigger magnet. Bigger magnets aren't necessarily stronger. You need to use a stronger magnet. You can increase the number of windings. In other words, put more coil, more wire inside the magnetic field. Okay? You could wrap the coil around an iron core. That creates an electromagnet. If you put an iron core in it, creates an electromagnet, that increases the magnetic field strength. You could also make sure that the angle between the magnetic field direction and the direction of the current is as close to 90 degrees as possible. When it gets to the top of its motion, so the coil moves to 90, it keeps going because of its momentum, but actually if it stopped there for whatever reason, heaven forbid, it wouldn't keep turning. There's no torque because it's outside. And also the magnetic field produced by the conductor and the magnetic field are then at 90 degrees to each other, and they won't interact. They must be parallel in the same plane. Okay, that's really, really important. Okay, So, but the first three, the first four, sorry, these four are the important ones, these four. Okay, stronger current, stronger magnets, iron core, more coils. Okay, now where do we use motors? Well, we use them in drills, CD players, washing machines, elevators, toy cars, hair dryers, fans, and the list goes on and on and on. Okay, whether it's DC or AC depends on the power supply. So something like a toy car will be a DC motor, where something like your washing machine would be an AC motor because we use it, we plug it in. A drill would be an AC motor. CD player would probably be a DC motor with a converter, and you can convert an AC current into DC current, but we're not going to worry about that now. Okay, so that was quick. So that's our motors done. So you're going to think about that for a little bit, and we're going to take a short break, and then we're going to see how much of what I just said to you went in. So you're going to take a short break, and I'll see you in a couple of minutes. So we've refreshed our brains. Okay, I know it's early, but we can do this. Okay, so here we have our question, and we're going to look at a motor. And it says to us, the essential components of a simplified DC motor are shown in the diagram. So we have a split ring commutator, we have brushes, and we have a coil. And they're showing you the direction in which the coil's moving. They're telling you it's doing this. So the AB part goes up, the CD part comes down. Let's look at the first question. And it says to us, what are the functions of the split ring commutator and the brushes? I'm giving you a minute to answer this question, and your minute starts now. Okay, so what is the function of the split ring commutator? There's a couple of ways you could have answered this question, okay, and you could have said to me to ensure that the coil travels in the same direction all the time, all of that sort of thing. But what they would want in your exams, okay, so this is the first question, and this is like the official answer, is that you have to write down that it's to reverse the direction of the current in the coil every half cycle. Okay, and that ensures that the coil turns in the same direction the whole time. Okay, so the commutator is very, 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 very important, okay, because it makes sure that the current in the coil keeps going, it reverses directions so that the coil keeps turning in one direction. That's the best way to put it. Okay, now the brushes, and I did tell you this is exactly what I told you. The point of the brushes is to make electrical contact. Okay, now please be careful here. This was a bit of contention for a while, but you have to use the word electrical. Okay, you can't just say to me to make contact with the commutator. It's to make electrical contact. That's the point, is to make sure that there's a complete electrical circuit. Okay, so it's to make electrical contact with the commutator. Okay, and the commutator is always connected to the coil. There's no issue about that, so let's not stress. Okay, but it's to make electrical contact. It's to make sure that our circuit remains complete. Okay, otherwise we won't have any current. Very important. All right, now same circuit. Okay, so here we have our circuit. Now they say to us, what is the direction of the conventional current? So will the coil experience a maximum, minimum, where it's shown, and state one way in which this turning effect or torque can be increased. So there's a couple of things. What is the direction of the current? Is it a maximum, minimum? And how can I increase this torque? Okay, I'm going to give you 2 minutes to answer those questions, and your time starts now. Gr12, I can just hear the arguments that are happening right now, more about what direction the current's going in than the other two questions. So, if we look at these, okay, the first question is, what is the direction of the conventional current? So now you have to look at the coil and you have to go, okay, now we're going to have to use either the left hand or the right hand, it doesn't matter. But they're asking what happens between A to B. So we remember that A to B is actually moving up and C to D is moving down with the way it's done. So if I use my right hand, okay, my north to south, my fingers point towards south, my thumb is the current, my palm is the force. So it's moving up, and as you can see, my thumb is pointing towards me. That means the current is going from B to A. If I use my left hand, my finger points towards south, my thumb points towards the direction in which the coil is moving, which is up, and my finger is actually pointing towards me as well. So in other words, the conventional current is going from B to A. Okay, that's the first question. Nice and easy, from B to A. Then, so this is from B to A. I'm not going to write it down. Then they say, will the coil experience a maximum or minimum turning effect? Well, the coil is flat in the magnet. This is a maximum. If it was vertical, it would be a minimum. So this is a maximum. Yay, maximum, nice and easy. Then they ask, state one way in which this turning effect can be increased. Well, we can increase this turning effect by, oh, look, it's not wanting to talk to me, by the things I told you earlier, increase the current, increase the magnetic field strength, put an iron core in the middle, or increase the number of turns, okay? Now what that does is it takes us to generators. And I'm so excited, I've got things to show you. Okay, generators use Faraday's law of induction, which you did last year and you did in a lot of detail, okay? And you used this horrible equation. I'm sure some of you remember it. I can hear the groans but you don't need to worry about it because we're not going to use this equation this year. Yay! But you still need to know the principle. So what I have here, okay, is I just want to remind you. So now I have one thing to, well, let's do the other one first. So what I want to show you, okay, so we have a simulation. I love it. So here we have a simulation. And what I'm going to do with this one is I have a magnet with a light bulb, and remember, this was Faraday's law of induction, is that if I move the magnet inside the coil, I can induce a current. If it's stationary, it's not going to do anything, okay? If it's moving, it does something, and it moves backwards and forwards, okay? If I swap the magnetic field around, all it means is it swaps the current. Okay, now if I add two coils, so now I want you to see, so I put my magnet in, I put my magnet out, I get quite a big current. Same magnet, less coils, I get a smaller current. Okay, over here, if I move it faster, I get a bigger current, just because it's fun. I shouldn't keep doing that. Anyway. All right, if I now do this one's a slightly different simulation, and I'm using this one deliberately because I want you to see that I can change how it works. Now here, we're going to talk about moving the coil inside the magnetic field, but this one moves the magnetic field. So by turning the magnets, and this is essentially what happens in a generator, I can create electric current, because as the magnetic field moves, and I'll show you the field, you can sort of see it. I think it's quite light. But as the field changes, you can see from the compass that it's keep moving, we get a current, okay? If I increase the number of loops, so I put more coils in, I get a bigger current because I've got a completely changing magnetic field. If I make the magnet turn faster, look, I get a very bright one. Now watch what happens if I make the loops smaller. My light bulb's not as bright because fewer loops mean a smaller amount of electricity is created, okay? This is basically how a generator works. So what we're going to do is we're going to do it in like proper science terms now, because that was fun. I love that. Anyway, so we get AC and DC generators, and whether we move the metallic coil, which is what we will generally talk about, or we move the magnet, it doesn't matter, but we will do the coil moving, okay? Remember that the coil moves inside the magnetic field, and what's important here is that mechanical energy is created from mechanical energy is converted into electrical. In a motor, electrical becomes mechanical. Now I take mechanical and I create electrical. Just like in a motor, a DC generator must have a split ring commutator, okay? It's a split ring commutator, and it has brushes. Now, when it comes to, and the thing with an AC generator over here, look, we have slip rings. So a DC generator has a commutator, an AC generator has slip rings. A DC generator means that when the current comes out of my generator, the current will keep flowing through the circuit in one direction, which is what we want. Or sometimes. In an AC generator, it goes backwards and forwards and backwards and forwards and backwards and forwards. Okay, goes in different directions. We're going to spend a lot of time in the next lesson looking at alternating current and calculations and all of that sort of stuff to do with alternating currents. We're not going to worry too much about that today. We're more concerned that you understand how we create the current, because that's the important part. Now, with a generator, how do we determine which direction the current's going to move in? Well, you can either do Fleming's right-hand rule, or you can do the palm rule, either way. Now, with Fleming's right-hand rule, your finger, this finger here, is in the direction of the magnetic field. Your thumb is in the direction in which the coil is moving, and your finger will now point in the direction of the current. Okay, so if I look at the motor I have over here, if we take out all the thingies that I've done, let's just take that away, and we think, well, which way is this current being generated? So let's just say that we're going to move this coil in. Oh, that's the eraser, it's not going to help. that way. Okay, so now it's going from north to south. This is why you move the page around, by the way, instead of your hand. So it's got to go point north to south, and it's now, so it's going this way. You see, now we just look silly. And it's going, and I'm pushed, so it's going from north to south. There we go. And I'm going to push it. Ooh, this gets very awkward when we move the page around. So point north to south, and I'm going north to south, and I'm going to push it that way. Ooh, this is why you move the page. See, I've got it on my page. Anyway, or we do the palm, it's better. So what's actually going to happen is my current's going to come out this way. It's going to come here. And I know you can't really see, I'm sorry. So it's going to go this way. Palm is just so much easier. See? So it's going from north to south, and I'm pushing it. It's going from north to south, and I'm pushing it over this way. Jeez, I'm not doing well. It's coming out. That's why we don't do it at an angle like that. Okay, and just like with a motor, when it's at 90 degrees, it's at the minimum. When it's flat, it's at the maximum. Okay, this one might be easier. So it's still, let's push it. Let's try and push it this way because we can. So it pushes this way, and it goes from north to south, and we're pushing it that way. And so my current's here. Oh, I'm doing well. I need to be able to move my page. Okay, because moving the page is just so much easier. Let's move on. Okay, now, where do we use DC motors? This is very important. Okay, we're not going to do that. DC motors are used in bicycle dynamos, torches, the ones that you shake or you wind. Okay, battery chargers, they all use a DC generator, sorry. AC motors are also alternators, which of course means they're used in cars. Okay, charges the battery in the car while the car's moving. Power plants, diesel generators, any of the ones you use at home are all AC generators, and microphones use AC generators, which is actually quite an interesting little concept along the way. Okay, we'll come back to the right hand and we'll do a question in a second where I can actually move my right hand in the correct way and not look like a complete idiot, which is why in your exam you'll move the paper. Okay, otherwise you'll look stupid. Anyway, so we're going to take a small break and then we'll do a couple of questions when you get back. So I'll see you in a couple of minutes. Okay, welcome back, grade 12s. And now we've got a picture that's not going to make us all look like idiots while we use our right hands. Okay, which is this hand, the one you write with, or if you're left-handed, the other one, probably the hand with your watch. Doesn't matter. So here's our question, and it says to us that we have a simplified sketch of a generator shown below. The first thing they ask you is it AC or DC? And explain your answer. Two effects of the output voltage. How can we make it bigger? And then they say, what is the position of the coil relative to the magnetic field when we get a maximum voltage? So here they don't even want to know what our current is. They don't care about the current. Okay, they're looking at other things. So this is a relatively easy question, but you've got to do a bit of writing. So I'm going to give you 2 minutes and your time starts now. So, grade 12s, how did we do? Hopefully not so bad. And what I'm hoping you get in here, grade 12s, is that with motors and generators, this is a theory thing. There's so little we can actually ask you. So the first thing they ask you here is the output voltage AC or DC? And give a reason. Well, we look at this and we go, look here. We have slip rings. It has to be AC. And your reason? There are I don't know what I was about to write there. There are slip rings. There's slip rings present. Okay? Slip rings mean AC. Next question says, state two effects on the output voltage if the coil is made to turn faster. Now, this might have been a little unfair because we haven't done everything yet. But the first thing you need to recognize is if I make it turn faster, I'm going to increase the voltage. Now, that voltage that's going to get increased is both the peak, and next week we're going to deal with this, and the RMS. Okay? So, it's a bit of a horrible question. So, we're increasing the voltage as well as increasing the frequency. In South Africa, we have a frequency when we generate electricity of about 50 hertz. In America, it's about 25. They use a much smaller voltage than we do. So you've got to be careful when you bring electrical equipment from the States. But we use the same as Europe, 50 hertz, okay? I'm not really sure why that is, but we do. Then they ask, what is the position of the coil relative to the magnetic field when the output voltage is at its maximum? Exactly like this. Parallel to the plane. That's when it's at maximum. When it goes perpendicular, it's at minimum. Okay? Parallel like this, maximum. Okay, now, the next question that we're going to do, hopefully we're not going to struggle with, because actually this is more about general knowledge, and it's quite important. It's going to come up, and you should have done something about this somewhere along the line in grade 8 or 9 or 10 or something. So in South Africa, the major source of electricity is coal-driven generators. Recently, society has become concerned about fossil fuels, like coal, as the primary source of electrical energy. Some business people have proposed that government should invest in windmills as an alternative source of energy. State one advantage and one disadvantage of using windmills over coal-driven generators. Okay, I'm not going to give you a lot of time over this one. In fact, I'm only going to give you a minute, so I want one advantage, one disadvantage of a windmill over coal, and your time starts now. So, you shouldn't have struggled with this one, grade 12s, okay? So things like, what are the advantages of windmills? Well, they don't create pollution. So advantage, no pollution as such, okay? So there's no pollution. Another advantage is that they use a renewable energy, okay? But the pollution's a good one because the environment's a big thing. The disadvantage, now disadvantages, this is very personal. So the biggest disadvantage is that there's no power if there's no wind. Okay, so you can't just put them anywhere. Port Elizabeth has wind farms now, which is great. Because Port Elizabeth is the windy city. Okay, Joburg wouldn't always be great for windmills, not for big wind farms. Okay, the next disadvantage that some people have, okay, is that they're unsightly. They don't look nice. That to me is not a big thing. Personally, I don't care about that because the environment is better. People also, another disadvantage is people have complained that birds and bats and those sort of things fly into the wind farms, so then they get damaged. There have been people who have complained in other countries about the noise a wind farm creates. That to me, I think, is also very personal. For me, the advantage of not having pollution and that they're a renewable energy source far outweighs their disadvantages. Okay, though they still can only be put in certain places. So we need to be careful there. Okay, all right. Let's do another question. I like this. So here we go. And we have diesel electric trains make use of electric motors as well as generators. They use both. The table below compares a motor and a generator in terms of energy conversion and underlying principles on which each operates. Complete the table by writing down the question number and next to each number the answer. So type of conversion and the principle of operation. And this one's a quick question. So I'm going to give you, what should I give you? 2 minutes, just because it's writing. So I'm going to give you 2 minutes and your 2 minutes starts now. Great. Grade 12, I'm really hoping you'll finish this question. I gave you really enough time to do this one. Now here, this is why this is so important to learn the section of work, because it looks a little different to some of the other stuff we've done, but it really isn't, because this is all theory. Because the first thing asks you, what is the type of energy conversion for a motor? Well, a motor takes electrical energy and converts it to mechanical, because we have to supply current, which then causes motion, okay? And if a motor is electrical to mechanical, then a generator is mechanical to electrical. It's the opposite, okay? Easy for the first two. Now the principle of operation. And this one becomes a little, ooh, what is it? But this I did right at the beginning when we looked at that flow diagram, or when we put all the words together on that one page. A motor, now wait for it, this is important, works on the principle of the motor effect. It's called the motor effect. I think we can all remember that. There are times when we go, oh, look, they gave us an easy one. A generator works on electromagnetic induction. Okay? Electromagnetic induction. Nice and simple. Learn these. This is such a nice way to summarize motors and generators. Okay, now, next question. We have an electric motor. There we go, simplified. And then it says, give a reason why the section of coil labeled BC in the above diagram does not experience a magnetic force while the coil is in this position as shown. I'm giving you 1 minute. Off you go. So, grade 12s. All right, let's do, first of all, BC. Okay, why does it not experience magnetic force? Simplest answer, okay, they accepted it, though it's not really what they were going for. Switch is open. There's no current in the circuit. Okay, so that's one answer you could have given me. But if the switch was closed, it still wouldn't be experiencing a force because BC is parallel to the magnetic field, and it can't be parallel. It must be at right angles. Remember, with your rules, everything is at right angles to each other. BC is not at right angles to the magnetic field. It's parallel to the magnetic field. If it's parallel to the magnetic field, it will not experience a force. Okay, so that's where we're going for that. Now, grade 12, like I said to you earlier, this is a theory section. Learn the theory, know it well. This becomes easy, easy, easy marks. Okay, next week we're going to do alternating current with calculations. Yay! And I have to say goodbye. So I'll see you next week.